Consider a hypothetical pharmacy AI system. It passes every test. Every single one. The evaluation suite is thorough language comprehension, dosage calculations, drug interaction checks, all scoring in the top percentile. Runs flawlessly in demos watched by executives, analysts, the press. The launch event gets good coverage. The deployment team ships it to production on schedule. For days, it works perfectly. Every input falls within distribution. Responses are correct, fast, reliable. The dashboard is green across every metric. Stakeholders celebrate. The engineering team moves on to the next release. Then, suddenly, it quietly misses a dosage recommendation. No error. No alert. No exception thrown. Just silence. A patient walks away with an incomplete prescription because the model produced something that looked fine enough that downstream systems never questioned it. There is no stack trace. No crash log. The failure was so well concealed by its own competence that no one noticed until weeks later, when a pattern emerged from patient complaints that should have been caught on day one. The scenario is hypothetical, but the structural risk is not. Microsoft Azure Agent Factory documentation acknowledges the structural reality behind it. Passing controlled evaluation tests does not guarantee functional readiness for automated enterprise action. The gap is real. It exists between the lab and the live environment, and it widens every time teams confuse a clean test suite with operational assurance. We have built AI that excels in controlled environments. But what happens when those systems enter real-world production? They often operate in near-correct ranges that many traditional monitoring tools were not designed to detect reliably. That is the quietest failure mode in software engineering because it passes most checks. It slips past automated gatekeepers, manual QA teams, and stakeholder sign-offs because it looks correct enough to be dismissed as acceptable variation. This is not a theoretical edge case. A model may produce acceptable outputs 99 times out of 100. Then generate silently incorrect results on edge case inputs that never appeared in training data. The difference between reliability and catastrophe is not always a dramatic malfunction. It is often this pattern of near corrects accumulating until they reach someone who cannot afford an error. Why do we keep missing these failures? Because we ask the wrong questions, and much of the evaluation ecosystem still rewards them. We ask, what is the highest accuracy this model can achieve? That is a question about ceiling performance. Rewards narrow. High-quality testing under ideal conditions. It measures how well a system works when every variable is controlled and favorable. It tells you too little about what happens outside that controlled environment, outside the test set, outside the distribution the model was optimized against. We never ask, how does performance degrade under real-world unpredictability? In deterministic software, an error is explicit and localized a function throws, or it does not. The stack trace points to the line number. The log records the exception code. Engineers triage, patch, deploy, verify. There is closure. An AI system works differently. The same model may produce acceptable outputs 99 times out of 100. Then generate silently incorrect results on edge case inputs that never appeared in training. Then on day 101, something shifts, a format changes slightly, a new vocabulary enters common usage, or a downstream system passes an unexpected payload. The model produces something wrong enough to be harmful, but plausible enough to not trigger any alert. The result is not a binary pass-fail. Quality falls across a range depending on input distribution and context complexity. Model capability metrics answer what an AI system can do. They do not measure whether it will do it consistently under real-world conditions where edge cases, tool call latencies. The result is not a binary pass-fail. Quality falls across a range depending on input distribution and context complexity. Model capability metrics answer what an AI system can do. They do not measure whether it will do it consistently under real-world conditions where edge cases, tool call latencies. Traditional reliability frameworks treat errors as binary because for decades they had to be binary. A server is up or down, a transaction succeeds or fails. A database query either returns consistent results or throws a constraint violation. For deterministic architecture, this model works beautifully. It is clean, auditable, and easy to reason about incident response. AI operates in shades of gray. Modern ML systems introduce stochastic behaviors whose correctness is often context-dependent or probabilistic rather than absolute. You can run a perfectly fine inference on what appears to be an identical input from yesterday and receive a different answer today. Not because the system broke, but because subtle contextual signals shifted enough to produce a divergent output. When results seem fine most of the time, but occasionally fail in consequential ways because degraded answer quality is not flagged by monitoring systems, we are not dealing with a simple broken system pattern. We are dealing with a system whose failure modes can be hidden by plausible output. And when organizations rely on traditional alerting infrastructure to catch AI errors, they miss the failure band where the most dangerous outputs live: answers that look correct enough to trust, wrong enough to harm. Some enterprises deploy gradual rollout strategies for AI endpoints, testing changes on a subset of traffic first. If anomalies surface, they roll back before customers see issues. Canary deployments with rollback capabilities that minimize exposure to ambiguous failure modes. This is an important pattern recognized by AWS. Well-architected generative AI lens as an established safety layer. Deploy broadly only after demonstrating operational readiness through controlled phased releases and explicit safety gating before automated systems touch enterprise data or execute operational workflows. Canary deployments alone are not enough. They catch obvious regressions, total accuracy drops, latency spikes, formatting breakdowns. They may not catch quality drift on their own, where the system answers shift from fully correct to mostly correct in ways that traditional dashboards and error rate monitors cannot distinguish from normal variation. Organizations that deploy AI endpoints without parallel confidence tracking infrastructure are effectively flying blind through operational uncertainty. Organizations increasingly need is monitoring designed for probabilistic systems, not only deterministic failure modes. That can include confidence-scored outputs checked against live ground truth samples, anomaly detection tuned to semantic drift, and continuous evaluation pipelines that probe alongside production traffic. Organizations update training datasets based on live production outcomes, not just historical benchmarks, closing the reliability gap between what the model learns in isolation and what reality demands in operation. Where these practices exist, they offer a stronger path toward operational stability than pre-deployment testing alone. The difference is not only better models, it is better verification infrastructure. Building it requires accepting that the old software reliability playbook needs significant adaptation for probabilistic systems. This is where the stakes become clear. Physical infrastructure power, compute, bandwidth, cooling has often been the first visible bottleneck for AI adoption. Many organizations deploying AI at scale must solve it early: racks, GPUs, networking, cooling, cost optimization. These are real, difficult, expensive problems. But they are solvable with conventional engineering rigor and capital investment. We have now hit the second bottleneck: trust. And it is harder to build than data centers. In this context, trust means systems designed to detect gray area failures and maintain operational integrity across deployment lifecycles. It requires judgment calls, adaptive monitoring, continuous human-in-the-loop validation, and governance frameworks that mature organizations spend years developing for deterministic systems, but have simply not had time to develop for probabilistic ones. In high-stakes domains, the risk is easy to see: a power grid AI could optimize for stability, but misunderstand a new weather pattern, creating cascading failures across regions. A hospital diagnostic AI could miss critical cases through ambiguous outputs, eroding confidence in AI-driven decisions that follow. A financial compliance AI could produce subtly misleading summaries of regulatory requirements, creating legal exposure that automated testing did not catch before deployment. Without these trust layers, organizations have a much harder time reliably deploying and governing high-stakes AI at scale. Physical infrastructure determines whether AI can exist. Reliability infrastructure determines whether it can operate safely once activated. The difference between shipping responsibly and shipping dangerously is not model capability alone, it is organizational trust infrastructure. This is not about fear, it is about responsibility. Organizations that build these trust layers now are better positioned to deploy AI systems with discipline and confidence than those relying on launch time testing alone. They reduce the blind spots that can lead to incidents, regulatory scrutiny, brand damage, and technical debt. Teams building this capacity today establish operational patterns, governance frameworks, and detection systems others may need years to develop. What do you do? Start with this every time your team says it passed all tests. Ask, but does it pass our world's tests? Test under degraded conditions. Test with adversarial inputs. Test with edge cases that resemble reality, not test sets. And build these reliability layers with the same rigor your architecture team applies to uptime. Because when AI systems fail silently, the only thing standing between competent operation and silent harm is the monitoring layer designed specifically to catch what ordinary alerts miss. As AI systems move deeper into healthcare, justice, infrastructure, and enterprise operations, we cannot afford to trust what we have not tested against real operational conditions. The gap between passing tests and proving readiness was never going to close on its own. It requires conscious design, and the organizations that build it will be better positioned to lead the next wave, not on model capability alone, but on operational reliability. AI readiness is not proven in the benchmark. It is proven in operation. For more systems-level analysis of AI deployment, reliability, and trust infrastructure, subscribe to Quantum Convergence AI and share the operational test your system still has to pass.